Practice question set number 24. Question number 1 says, in a laboratory experiment, a microwave generator is used to produce a beam of monochromatic microwaves. What does monochromatic mean? One color, one frequency. Although it doesn't really matter, right? If we have a question where we have polychromatic or multiple colors or multiple frequencies, we know that it doesn't make it any harder, really. It just seems a little bit harder because we've got all this different looking interference pattern going on. But in the end, all we do is pick a color, pick one color, one frequency, and run with it. And it turns into the same question as we have right here. These waves, these monochromatic waves, are incident on a series of metal tubes that forms a diffraction grating. The metal tubes are spaced 1.80 centimeters apart. What are we given there? If the tubes form the diffraction grating and the tubes are 1.80 centimeters apart. This is what? This is D. This is little d, yeah. So little d is 1.80 centimeters. Now we're going to circle that centimeters just because, well, that's not the standard units here. Now, I don't know if anybody noticed this when you were working on this question or not. The spacing here is pretty big compared to what we're used to seeing, right? We're used to seeing like about 10 to the minus 5 meters for the spacing there, right? Okay, this is 10 to the minus 2 meters, so much, much bigger. Can anybody suggest maybe, given the context of this question, why maybe the spacing of these tubes is a lot further, is a lot further apart than we're typically used to seeing? Isaac? Yeah, because we're dealing with microwaves, and microwaves have a lower frequency and a higher wavelength, right? So that means that we can get away with using spacing that's bigger and still make this work. If we were to use this spacing with visible light, it wouldn't work. We wouldn't see an interference pattern. Okay, we have to have a much smaller spacing. Now, you guys don't need to be familiar with that, so I wouldn't lose any sleep over that. Okay, but that's why, in this case, we can use much more spacing than we typically see. All right. When the microwave signal passes through the grating, the receiver placed 52 centimeters from the grating detects a maximum signal. What would that 52 centimeters thing be? What variable would that be? The receiver placed 52 centimeters from the grating. What is that receiver acting as? That's acting as our screen, right? We can't see microwaves on a piece of paper or on a white screen, so we have to have some kind of electronic receiver. Okay, that's what we got here. So this is going to be the value of L, right? This is from the diffraction grating to the screen. A first order maximum signal is detected at positions 1 and 2 as labeled on the diagram. So this would be our central maximum. We'll make this 0, and then position 1 and position 2 would be n is equal to 1 because we've got our first order maxima there. And it says the angle from the central maximum to either one of these is 49.8 degrees. So I'm going to label this one as 49.8 degrees. What would the value of n be there? Yep, 1. N is going to be equal to 1 because we're dealing with the central maximum and the first order maximum. Now we could have done it on the other side as well. It doesn't really matter. N is going to be equal to 1 in both cases, and the angle would be 49.8 degrees in both cases. That's a pretty big angle, right? 49.8 degrees. What does that tell us before we even look at the question? We have an angle of 49.8 degrees in this. It tells us that we cannot use that second equation, right? That second equation is only valid for angles less than 10 degrees, and we've got an angle that's dramatically bigger than 10 degrees. Okay, the good news is we have enough information to not even bother trying that other equation, so there's no real reason why we would want to use that other equation. But even if we had that thought, it wouldn't be valid here. We're going to say lambda is equal to d sine theta over n. And we've got all those variables there. D, theta, and n. Look, we do have L. Do we need that? No, we don't, right? We don't. I said there's no reason for us to try. Lambda is equal to xd over n times L. There isn't really any reason because we have an angle given to us. And when we have the angle, why would we bother using the approximation when we have an equation that always works? But in the end here, we do have variables given to us that might trick us into wanting to use that equation. We have the value of, no, I guess we don't have x, do we? We don't have x. We do have n L, we do have L, so we're still missing a variable there. Even if we try to use that equation, which isn't valid, we couldn't use it, of course, because we're missing the value of x. So back to this one, which of course we knew we were going to use in the first place here anyways. D is 1.8. Should I convert that? Now this time I'm actually not going to convert it. Okay, the standard is to use meters here, but if we have meters on the left side and the right side, what happens to the meters? What happens to the units? If we have the same units for this variable and this variable, the units end up canceling out, right? Now, typically, we want you to do these questions in meters, but since we're looking for an answer in centimeters, and we've got our distance in centimeters, you might want to stick with that. Now, if you'd rather go to meters, go to meters. And then what do you got to do when you turn around and solve for wavelength? Convert it back to centimeters. So it ends up being a couple unit conversions that you don't have to do. But if that makes you more comfortable, then go ahead and do that. D is 1.80 centimeters, sine of 49.8 degrees, and N is 1. So we're just going to say 1.8 times sine 49.8, and then of course that's divided by 1, gives me 1.37. Yeah. We just record that as 1.37 centimeters. How many people got that? Okay, good. Now the second question is a little bit ickier, and this is what I was going to, when I was handing this out as a quiz, I was going to mention something about here just because one of the terms you would be familiar with by the time we finish the year, but we wouldn't be familiar with at this point. And that's the difference between a continuous spectrum and a bright line spectrum. We've mentioned this term before, a continuous spectrum, but we haven't mentioned the term bright line spectrum. The difference between a continuous spectrum and a bright line spectrum is simply that the continuous spectrum is the rainbow, so it's one color transitioning into the next color, right? Whereas the bright line spectrum is individual colors, like individual, here's a red line, here's a blue line, here's a violet line, and so on and so on and so on. So when we look at these observations that were observations of optical phenomenon, they look like they're kind of paired up, right? 1 and 2 look like they kind of go together. 3 and 4 look like they kind of go together. 5 and 6 go together. And 7 and 8 go together. We want to know which 4 observations can be produced using a triangular glass prism. When we shine white light through a triangular glass prism, what do we get? What do we get? Do we get a rainbow, or do we get individual lines? We get a rainbow, right? We get a continuous spectrum. So with the triangular glass prism, we would absolutely get observation number 1, a continuous spectrum. Now, let's look at 3 and 4. If we had monochromatic light, one color of light, let's say red, would we get an interference pattern, or would we get a single red line, a single line through a prism? Here's my prism. I'm shining red light through that prism. What do you get on the other side? An interference pattern or a single line? A single bright line, right? Does that make sense? So it would be observation number 4 for a triangular glass prism. Now let's look at 5 and 6. The apparatus bends red light through a smaller angle than it bends blue light. Does it? Yeah, it does. Actually, a prism bends red light through a smaller angle than it does blue light. You can see that on the poster on the sideboard, or you can just remember the diagram that we showed you in class. So that would be 5, 1, 4, 5. 6, by the way, we could change this question to make 6 correct. The apparatus bends red light more or through a larger angle than it bends blue light if we made it a diffraction grating, right? If diffraction grating, of course, is opposite. Instead of Roy G. Biv, it's Viv G. Orr. And finally, 7 and 8, the apparatus produces a single spectrum when white light is incident upon it, or multiple spectra when white light is incident upon it. When we shine white light on this prism, we get a spectrum on the other side, right here. But it's only one. It's only one spectrum, right? So that would be a 7. Now, a diffraction grating does produce multiple spectra because you get that central maximum, which is that white light, the white line, the maximum, the white maximum. And then you get the first order maximum, which is VIBGYOR, and then you get the second order maximum, which is VIBGYOR, and the third order maximum, which is VIBGYOR, and so on and so on and so on. So you find that each maximum ends up being what we would call a spectrum, right? So you get multiple spectra with a diffraction grating versus one spectrum with a prism. So the answer here is 1, 4, 5, 7, right? How many people had 1, 4, 5, 7 for this? Okay. How many people had an issue with number 1, with the first one, with a 1 or a 2? Okay. What was the other one that people had trouble with? Okay, tell me something else that you got wrong on this besides the first one, which I would kind of anticipate because I should have explained that term, bright line spectrum.